Now, before talking about memory management, I mean how the process are managed by the operating system in the main memory, let's see how a process is created first, okay, and then we shall examine how it is loaded. So there are various issues here. They are very small issues. The problem with this is, I'll just tell you, these are very small things and you cannot neglect them completely, nor you cannot put lot of effort in this in understanding how a process is loaded and how a program is loaded and made into a process. So what happened is, in the compiler design textbooks, they just overlook it, saying that in operating systems you'll see it, and in operating systems they'll say that it is out of the scope of the book. So no textbook has actually given much weightage to these important things. So what I did is I read some other materials and other textbooks, especially on these topics, so that they will be very clear for you. And please don't refer to any textbook whatever I'm going to teach, because no textbook is actually containing complete, they are not going to show everything, and moreover it will be confusing. So what I'll try to do is, I'll try to explain these concepts in a simple and easy manner, and you please make a note of it. And you might not understand this in the middle of the video, so let the video completely finish, then you'll understand it. Okay, don't read anywhere, just whatever I'm going to teach is enough, and you can answer all the gate questions with this content. And even if you get confused, keep going. Okay, see this. I'll start from the basics. I assume that you don't know anything, and I'll start from the basics. Let us take a small C program. And how do you write a C program? Either in if you are talking about Linux or Unix, you'll use Vim, right? Vim or VI editor, or some text editor, right? So you open a text editor, and then you write the entire C program, and then you'll give the C program to the compiler, right? And what will compiler do? Compiler will produce output assembly code, assembly language code, right? And now this assembly language code will be given to the assembler, right? And now this assembler is going to produce you some code which is called as object code. Object code, it is also called as object code, which is not actually executable code. It is in the machine language only, zeros and ones, but then you cannot directly execute it, right? I'll tell you why. So now this object code, this is the object code which is going to be produced as the output of the assembler. But then when you write it at your home or in your laboratories, and compiler will be generating you the directly executable code. But what happened here is, in those systems which you are using, the compiler is actually combined inside with assembler along with loader and linker. So all the modules are kept together in the compiler software itself. So when you are calling GCC, you are actually not just calling the compiler, you are calling the compiler and then assembler and then linker and loader. But purely, if you talk about only the detailed parts, compiler is supposed to give you only the assembly code, and now assembly code will be taken by the assembler, and you know what? Assemblers will be different for various platforms, which means every computer, every hardware will have its own assembler. Therefore, depending on the hardware you are working on, the corresponding assembly code will be generated by the compiler. Now that corresponding assembly code will be taken by assembler, and that will be converted to the object code. So either the text program, so once this is done, so you are going to call the compiler. Once this is done, your object code is going to be present in the hard disk. Okay, so later what we should do is, this object code contains like this. Okay, I'm just going to depth of what an object code is. It is not required for gate, but if you have to understand this thoroughly, I just have to do it. Okay, so you need not by heart about this, just see what an object code looks like. If object code file is going to look like this. Object code is going to contain various parts like this. First thing is, it will contain some header, and the header will say what are the various parts present in this object code and their pointers, and it will contain code segment, or you can say it as text segment. Text segment or code segment, right? It is nothing but the set of instructions, and then it will contain data segment. Data segment will contain the data elements present, and after that it will contain something called as relocation information, and then symbol table, and then finally it will contain something called as debugging information, debugging info. Let's see what each one really means here. So when you compile a program, and assembler is going to give you a file like this, what it will say is, this header will say where the text segment is going to start, a pointer to it, and it will say where the data segment is going to start, and it will say where the relocation information is there and symbol information is there. It is nothing but like an index. If you have a textbook, there the index page will contain at what page number each topic is in, right? Similarly, this one will show you or tell you what are the places at which each information is present, so that later for other softwares it will be useful to directly go into those segments if they want to get into them, right? And now this text segment will just contain the instructions, and the data segment will contain whatever data you have used, right? For example, you might have used something like constants, right? Then they are going to be present here. And this relocation information this is important. So what is relocation is, before talking about this relocation information, I should talk about relocation first. There are actually three things, three main things that we should be talking about. One of this is relocation. So watch this. Relocation information is this. So whenever you try to write a program, I'm talking about the text, high level text, we use the symbols, right? We generally use symbols to specify many things. For example, we use labels, right? Maybe let's say there are some symbolic notations we use. And now when this symbolic notations are given to this compiler, and when the compiler has given it to the assembly code and assembler is going to convert it to this, then what happens is these symbols have to be replaced with numbers. So we assume that it might not be right. So what the compiler or this assembler will assume is, they assume that the program is going to start with line number 0, and they are going to number all the instructions with those line numbers. For example, what I mean to say is, let us say you have instruction 1, instruction 2, instruction 3 like this. Let me take a big example. What is relocation is like this. Let us say this is a program in which you have instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, right? Then at user, what he will use is, he will use numeric, some symbolic constants, right? So he will say somewhere, go to label L1, right? So even if you don't write go to statements in your high level language, the output of the compiler is going to write it. So compiler is going to convert it into intermediate language, some assembly code, and assembly code is going to contain go to L1, something like this, right? Then what happens is here, L1 will be some number here, L1 will be some label here, right? Then when this code is converted to object code, all the labels are going to be replaced with the addresses. If L1 is present at line number 4, here it is going to contain line number 4, right? Go to line number 4. So fine, it works fine as long, when you assume that the first instruction is at address 1 and address 2, let us say first instruction is address 0, address 0, address 1, address 2, address 3, address 4, then go to 4 for the label L1 is going to work fine as long as this program is going to be loaded starting at address number 0. But then in most of the systems, initial part of the RAM is going to be dedicated to operating system. Even if it is not dedicated to operating system, there might be some other process which is already running at address number 0. So all the process cannot be loaded at address number 0, right? So what should be done is, when you are going to load it on the memory, in the main memory, the same process, if this program has to be loaded in the main memory, it might be loaded anywhere else, right? So which means it might be loaded at an address 100,000. Let us say 100k is the starting address. Then all these addresses have to be changed, which means this address is going to be 100,000 plus 0, right? 100k plus 0 plus 1 plus 2 plus 3 plus 4, right? Therefore now the line go to 4 has to be converted to go to 100k plus 4, right? This is called relocation. Got it? And this is called relocatable address. The reason is this has to be changed, that is why it is called relocatable address, and this process is called relocation. Relocation is nothing but converting one address to the other address is called relocation, and the original addresses, these are all called as relocatable addresses. Relocatable addresses, and the final address which we get after we load the process, this program into the memory, this is called as absolute address. Absolute address. Right? Now the problem with this assembly code output is, if the assembler knows that, if the assembler is very sure that the program is definitely going to be loaded at some particular address in the main memory, then it can directly generate the object code in such a way that every address reference in the program is going to point to the actual address, which is nothing but the absolute address. But the problem is we can never be sure, or at the compile time itself, it is also called as compile time. Now if you put everything together, this is also called as compile time. Now during compilation we will never know. In case if we know, it is fine. During compile time we never know where a program is going to be loaded. Therefore what we do is, we don't try to assign any real addresses to the instructions wherever they are occurring. We just try to assign some relocatable addresses, assuming that the program is always going to start at address number 0. We number the instructions in such a way, and then accordingly we are going to put the addresses, right? And later at various times they have to be changed, right? If you directly allocate that final address, if you directly allocate that final address, the absolute address, at the compile time, that is called as compile time binding. But then it is very difficult to know when you are compiling a program where a program will be loaded, because even if you assume that a program is going to be loaded at some address, the chances are that when you try to actually load it, there might be some other program already executing. Therefore you cannot overwrite on that. So it is rarely used, it is never used. Very long, long back, in 1940s it has been used. Later it is not used. In 1947, 1950s it is used. Later it is not used. Now what happens is, a program is going to contain many such relocatable addresses. So this particular part is going to contain, is going to specify what are all the parts in your program where I have used the relocatable code. Why is it, relocatable addresses? Why is this important is, later when you try to load it into the memory, actual memory, you are supposed to use this information and convert every relocatable address into absolute address. If you don't have this information, then we cannot find out where all we have to change the address, where all we have to perform the additions like this. Got it? Here it is a simple addition, right? So without this information we can never know it. So understood this? The output produced by the assembler, or in fact this compiler plus assembler, the output produced is going to contain relocatable addresses which we have to change before we load into the memory. Otherwise what happens is, see this, if you don't change it, then it is going to say go to line number 4. But now once you load it into the memory, the line number 4 is not actually line number 4. The line number 4 might be some other process, or in fact it might be operating system. Then your process is trying to access the code which it is not supposed to access, and that will lead to a trap. What is a trap? We shall see it later, okay? Or which is the error. You can think of it as an error. You are not supposed to do that. It is like this. You are supposed to use only your house, right? You are not supposed to use the other house. Every process has its own house and it should not look into the other house. Got it? So now this relocation information is going to help you in finding out where you should be adding the addresses. Fine, that is done. And next thing is symbol table. So what does the symbol table contain is, it contains every symbol that you have used in your program. For example, int ABC are symbols, or let us say printf is a symbol. So every name is a symbol. So it is going to contain all the symbols. Now why is this important is it will show what are the variables that your program contains, as well as what are the procedures that your program has defined, right? And then what are the procedures you have called. So what I mean to say is like this: the symbol table might contain various parts. Let us say you have defined a function minimum, right? Then min is a symbol. Let us assume that you have defined a symbol called minimum. The symbol table will contain like this, something like this, right? Minimum is a function which you might have defined. Then in that case, if we have defined the function inside this, then the symbol table will contain the symbol and the address in which it is present, which means it will even give you the relocatable address. So it may say that it is present at line number 100. Therefore you can understand that wherever you are going to call this function minimum, you are supposed to go to line number 100 and execute the code. Sometimes what happens is there will be some functions which you have called that they are called as external references. There will be some functions which you have called, but then you really don't have the code available in your own program or in your own object code. So the simple example is printf. So you don't write the printf code, isn't it? But then you will call the printf program. So when you call the printf object or the program, it is actually unresolved. Therefore, we don't know where it has to go, right? Let us say printf, scanf, all these functions, right? So these are all called as unresolved symbols. So symbol table is important because it will say what are the functions which are defined in your what are the functions which are defined in your own program, as well as what are the variables which are defined in your own program, and what are the functions or variables which they are not defined in your program but you are referring them from other program. Then what happens is before you try to run it, you are supposed to fix them. See, if there is a line called printf, right, then what happens with that call printf is, if there is a line called printf, then it is nothing but we should go to that corresponding line number, but then we don't know where to go. Therefore you have to resolve it. So unresolved symbols, all of them have to be resolved before you is relocation. Relocation is converting the addresses to absolute addresses. That relocation is done by this loader, and these unresolved symbols have to be resolved. They are done by linker. Okay, fine. Let's put it separately. I'm not going to talk about linker and loader now. It will be confusing. Let's do it in simple manner. Okay. So now your object code is going to contain this entire information. This entire information is going to contain what are the symbols, what are the addresses you should change, and what are the symbols you should resolve later. Both are different. These contain the addresses which have to be resolved, and these contain the symbols which have to be resolved. And then debugging information is not required for you. So why is debugging information used is for this. Sometimes you might use debugging programs like GDB. If you have used GDB, you will be aware of it. So you will try to find out what a variable, how a variable is keeping on changing. You might try to find it out. So that is called as debugging, right? So in case of that debugging, if you are using it, that debugging program, once we have replaced the symbols with some addresses, then even though you are trying to trace a symbol, that symbol name will not be there at all. Then this information is going to help the debugger in order to find it out. Okay, fine. So it is going to be difficult, confusing. So act as if there is no debugging information, because we don't need it really. We don't need it in any of the subjects for Gate. So debugging information not present. I didn't tell you anything, leave it. So now these two information are going to be present in the object code. Now let's continue about what happens. I think you understood what relocation is, right? So only my concern is you should understand this relocation perfectly. So relocation is when you are compiling the program, we don't know where the program is going to be loaded. Therefore, we assume that it is going to start at address number 0, and accordingly we'll number all the instructions, and therefore any symbolic reference like go to L, like this is going to be resolved using that particular address. But when you load it into the memory, it is going to create a lot of problem because line number 4 is now not in your memory, right? So depending on where you are going to load it, you are going to change it. Now this entire procedure is called as relocation, and the initial address which is used is called as relocatable address, and the final address which you get is called as absolute address. So before you load a program, you are supposed to convert every relocatable address into absolute address. That is what my intention is, by explaining all this. Now let's see what should be done before we actually run the program in the first place. So now I told you that your program is not just going to contain everything which is required to be executed. It is rarely a case. Rarely you'll write a program which does not contain printf, scanf, isn't it? And every program, almost every program you could think of, they will try to call some functionalities which are not already present in your program. So every program is going to be written in such a way that it needs to take support from other programs, right? Then we are going to take this object code. Let us say that is your object code. Object code. I'll just take an example. Let us say this object code, let's call it as A, and now this object code is going to call, it is calling object code B and then C and then D, right? And let us say there is some other object code, object code B. This is also some object code like this, right? And let us assume that it is calling D and E. D and E, and C, D and E say that they are all system libraries. Libraries are nothing but, what happens is many times we need some functionalities, and it is not just we who need it. Along with us, many others will also need the same functionalities. Then it is, it is useful if many people need some functionality. Then it is useful if you write it at one place and then compile it and make it available for everyone, so that they will not again do it. It is nothing but, we don't want to reinvent the wheel. If something is already available, we just could use it, right? And all such parts are present in the library, right? And so the library is going to contain all the others. Let us say library is going to contain the modules. One is whatever modules we don't have here. So this is written by a user, this is written by a user, and both are compiled independently, which means this is compiled independently and this is compiled independently, and already the libraries are compiled independently and they are present separately. And let us say C, D, E, and various functions are present here, F, everything, right? And now these will be given to the linker. So linker will take your program and then it will take all the supporting programs that you need, right? And now it is going to give us again one more executable code, or you can call it as again the object code, no problem. So let me call it as executable code. So executable code, let's not use that word as of now. Executable code means you need not do anything. You should be able